Hello everybody, my name's Iman. Welcome back to my YouTube channel. Today we're continuing our lecture on thermochemistry. We've made it to the 8th objective, and the topic that we're going to cover in this objective is Hess's law. Now, Hess's law is a fundamental principle in thermochemistry that deals with the enthalpy changes of chemical reactions. Now, we've talked about enthalpy, and we've stated that enthalpy is a state function. That means that anytime a chemical reaction or physical change occurs, the magnitude of enthalpy depends only on the initial and final states and not on the pathway taken. Now, if there are different pathways that a process can follow, the overall enthalpy change must be the same regardless of the pathway. So one way to state this information is with Hess's law, which says that the total enthalpy change for a process is the same regardless of whether it occurs in one step or in many different steps. So for example, let's consider the formation of lead-4 oxide from lead and oxygen gas. If lead reacts with sufficient oxygen, then this reaction could occur directly in one step, and the associated enthalpy change for this reaction is minus 277.4 kilojoules. Now, the same overall reaction could also be carried out in two steps by following a different pathway. So first, lead can react to form lead-2 monoxide, and then that lead-2 monoxide can react with additional oxygen gas to form lead-4 oxide. Now, the enthalpy change for the first step of this reaction is minus 217.3 kilojoules, and the enthalpy change associated with step 2 for this reaction is minus 60.1 kilojoules. If we sum this up, the total enthalpy change is going to be minus 277.4. So notice that the overall enthalpy change when lead-4 oxide is produced in the two-step pathway is the same as the enthalpy change from that of the one-step pathway. And so this confirms that the overall enthalpy change is independent of the pathway taken. And by using Hess's law, we can determine the enthalpy changes of reactions that are difficult to measure directly by breaking them into a series of steps with known enthalpy changes. And this powerful tool really allows chemists to manipulate and combine reactions to find unknown enthalpy changes. Now, in addition to understanding Hess's law in terms of enthalpy changes over multiple steps, we can also express Hess's law using bond enthalpies, also known as bond dissociation energies. Bond dissociation energy is the average energy required to break a particular type of bond between atoms in the gas phase. So this approach involves calculating the total enthalpy change of a reaction by considering the energy that's required to break all of the bonds in the reactants, and then the energy that's released when new bonds form in the products. Now, to elaborate, the enthalpy change of a reaction, it can be determined by the formula that you see written here. In this equation, we have our sum term, delta H bonds broken. This represents the total energy that's required to break the bonds in the reactants. This is subtracted from this sum term, delta H bonds formed, and this represents the total energy released when new bonds are formed in the products. And so by using bond enthalpies, we essentially apply Hess's law to the individual bond breaking and bond forming steps of a reaction. And by summing the enthalpies of the bonds broken and subtracting the bond enthalpies of the bonds formed, we obtain the overall enthalpy change for the reaction. And this method, it highlights the additive nature of enthalpy changes. And again, it reinforces the idea that the total enthalpy change for a process is independent of the specific steps taken. And that aligns perfectly with Hess's law. Now, the next thing we want to talk about is a couple of terms regarding enthalpy. Thus far in our lecture, when we discuss change in enthalpy, we write delta H. But I want to be a little bit more specific and also explain standard enthalpy of reaction, which is written as so, and standard enthalpy of formation, which is written as so. So let's start with first discussing the standard enthalpy of a reaction. This is the enthalpy change when a reaction occurs under standard conditions. That means 1 atmosphere pressure at 298 Kelvin, with all reactants and products in their standard states. This means that this is the physical state in which the substance is most stable under standard conditions. Now, this value is typically expressed in kilojoules per mole, and the standard enthalpy of a reaction can be determined using the standard enthalpies of formation of the reactants and products. And that leads us into discussing the next term. What's standard enthalpy of formation? This is the enthalpy change when 1 mole of a compound is formed from its elements in their standard states under standard conditions. And again, let me repeat, that's 1 atmosphere and 298 Kelvin. Now, the standard enthalpy of formation for an element in its standard state is defined as 0. And this concept is crucial because it allows for the calculation of the enthalpy changes in reactions using tabulated values for various compounds. And we're going to get back to that here in a second. But now the question could become, well, what is the relationship between standard enthalpy of reaction and standard enthalpy of formation? To calculate the standard enthalpy of a reaction using standard enthalpies of formation, we can actually use Hess's law. Hess's law states that the total enthalpy change of a reaction is the same regardless of the number of steps in the reaction. And the enthalpy change of a reaction can be calculated like so. It is going to be the sum of the standard enthalpy of formation for the products subtracted from the sum of the standard enthalpy of formation for the reactants. This formula accounts for the sum of the standard enthalpies of formation of the products, each multiplied by their stoichiometric coefficients, minus the sum of the standard enthalpies of formation of the reactants, each multiplied by their stoichiometric coefficients. Now, I really do want to elaborate a little bit more about standard enthalpies of formation because this is an extremely important topic to conceptually understand because it allows us to determine the standard enthalpy change for a reaction without actually performing a calorimetry experiment. There are millions of chemical reactions that we can do, and it would be impractical to try to record the standard enthalpy of a reaction for each single one. In addition, many reactions are not conducive to calorimetry measurements. So for example, consider the formation of diamond from graphite. This kind of reaction, like so many others we encounter, cannot be easily carried out in a calorimeter. And so it would be very useful to be able to determine the standard enthalpy of a reaction without doing a measurement. And this is where standard enthalpies of formation come into play. They allow us to do just that. So again, standard enthalpy of formation is the standard enthalpy change that occurs when 1 mole of a substance is formed from its elements in their most stable form. And an important idea that's related to standard enthalpies of formation is that think of it as a shorthand for a particular thermochemical equation. Anytime you have the standard enthalpy of formation for a particular substance, you can always write a corresponding thermochemical equation where the substance is formed from its elements. Now, we're going to see this at play in a couple of example problems that we're going to hop into next. So keeping those definitions in mind, as well as the idea of Hess's law, let's approach these two practice problems. For this first problem, we're given the following three thermochemical equations, and we're asked to calculate the enthalpy change for this reaction. So here, we're going to use Hess's law, which states that the enthalpy change of a reaction is the sum of the enthalpy changes of the steps that lead to the overall reaction. So what we're going to have to do is manipulate the given reactions to derive the target reaction. So the first thing that we want to start off with is looking at our target reaction and noticing what our reactants are and what our products are. So here in our target reaction, we have carbon in solid form, graphite, plus 2 moles of hydrogen gas that react together to give us 1 mole of methane gas. Now, the second thing we want to do is look at our three given thermochemical equations and just really quickly pick up on the species that are present. So looking at these three thermochemical equations, we see methane, we see oxygen gas, carbon dioxide, water, we see carbon in solid form, graphite, more oxygen, more carbon dioxide, hydrogen gas, more oxygen gas, and water. Okay, so right off the bat, considering what our target reaction is and what the three thermochemical reactions were given, we're quick to note that we have these three reactions that we're going to combine together in a way that's going to have to eliminate the intermediates. Those intermediates are the oxygen gas, the carbon dioxide, and the water. We need those to cancel out because they do not appear in our target reaction. So again, we have three reactions and we need to combine them in such a way that the intermediates cancel out, leaving only the reactants and products in the target reaction. Now we can start looking at each reaction in depth one by one. Reaction A, we have 1 mole of methane reacting with 2 moles of oxygen gas to give us carbon dioxide and 2 moles of water. Now here, methane is the only species that appears in our target reaction from reaction A. And here in reaction A, it's the reactant, but in our target reaction, it's the product. So the first thing that we're going to think that we need to do with reaction A is reverse it. Okay, so we're going to write it in reverse and see later on if there's anything else we need to do with it. But we're going to start off with this simple change. We're going to reverse the reaction so that when we add it with B and C, methane is in the products just like it should be for our target reaction. So I'm going to go ahead and write this in reverse. Carbon dioxide plus 2 moles of water give us 1 mole of methane plus 2 moles of oxygen gas. Now, there's a consequence to us reversing this reaction. Delta H, the sign has to change. So for this reverse reaction, delta H is going to be positive 890.4 kilojoules per mole. Okay, so that was reaction A. Let's go ahead and look at reaction B. In reaction B, we have carbon in its solid form, graphite, plus oxygen gas gives us carbon dioxide. Now, the only species that's present in reaction B that also appears in our target reaction is carbon in its solid form. And in reaction B, it's part of the reactants, just like it is in our target reaction. So as of now, we're not going to change reaction B at all. We're just going to go ahead and rewrite it down here. All right, we have carbon in its solid form plus oxygen gas gives us carbon dioxide. Delta H is still minus 393.5 kilojoules per mole since we did not manipulate this reaction. Okay, now for the last one. All right, Reaction C. We have 1 mole of hydrogen gas plus a half mole of oxygen gas gives us water. Now, the only species that's present here that's also in our target reaction is hydrogen gas. And notice that they're both in the reactant, so that's good. We're not going to reverse this reaction. But there is an issue. In reaction C, there's only 1 mole of hydrogen gas, but in our target reaction, there's 2 moles. So we're going to go ahead and multiply this reaction by 2. Now, when we multiply the reaction by 2, we also multiply the enthalpy change by 2. So let's go ahead and rewrite this reaction now that we've multiplied it by 2. We have 2 moles of hydrogen gas plus 1 mole of oxygen gas, and that gives us 2 moles of water. And now the delta H is going to be minus 285.8 multiplied by 2 kilojoules per mole. Wonderful. So we've played around with these reactions a little bit just to make sure that we have our desired species in their appropriate places with their appropriate mole ratios. Now, what we want to make sure is if we were to add these 3 reactions together, would we be able to cancel out and get rid of our intermediate species, oxygen gas, carbon dioxide, and water? And in order to say that those cancel each other out, we would need the same amount of oxygen, carbon dioxide, and water on the reactant side as we do on the product side. That way, they would cancel each other out. So let's start to look at our first reaction. All right, reaction A has carbon dioxide as a reactant, 1 mole of it. And our reaction B also has carbon dioxide, 1 mole of it in the products. That's perfect. That means carbon dioxide cancels out. What about our water? We have 2 moles of water in reaction A on the reactant side. And then if we look at reaction C, we have 2 moles of water in the product side. Perfect. That means that water is going to cancel out. Now, the last species that we have to worry about is oxygen. If we look at reaction A, we have 2 moles of oxygen gas on the product side. If we look at reaction B and C, we have oxygen gas on the reactant side, 1 mole in reaction B and 1 mole in reaction C. So we have a total of 2 moles of oxygen gas on the reactant side, 2 moles of oxygen gas on the product side, and so therefore they cancel each other out. Now what we're left with if we add up these reactions is carbon in its solid form plus 2 moles of hydrogen gas give us 1 mole of methane gas. That's perfect. That's exactly what we need. So that means that we manipulated the 3 thermochemical reactions we were given appropriately. And that means that we can go ahead now and add up the delta H values for each of these 3 reactions and get the delta H for our target reaction. So that means that we have 890.4 plus minus 393.5 plus 2 times minus 285.8. All right, now we can go ahead and do some approximations here so that this math is easy. We're going to approximate this to 900. We're going to approximate this to minus 400. And then we're going to approximate this as 2 times minus 285, and that is minus 570. So again, we have 900 minus 400 minus 570, and that gives us a total of minus 70 kilojoules per mole. That is the correct answer for this example problem. Wonderful. So we were able to solve this with our knowledge of Hess's law. Let's go ahead and move into the second example problem. This second problem asks us to calculate the enthalpy change for this reaction. Carbon in its solid form reacts with 2 moles of hydrogen gas to give us 1 mole of methane. This is exactly the same reaction that we just worked with in the first problem. But here we're given a different set of information and asked to use that information to calculate the enthalpy change for this reaction. we're given the bond dissociation energy of a hydrogen-hydrogen bond that is equal to 436 kilojoules per mole. And we're also given the bond dissociation energy of a carbon-hydrogen bond, and that is equal to 415 kilojoules per mole. We are also given the enthalpy of formation for gaseous carbon, and that is equal to 715 kilojoules per mole. Now, to find the enthalpy change for this target reaction, we're going to have to use the bond dissociation energies and the enthalpy of formation. And the key here is that the target reaction is going to be split into 3 steps involving the formation of methane from its elements in their standard states. So this is going to require us to use our knowledge of standard enthalpy of formation. So the first thing we're going to do is we're going to break down the reaction, and we can break it down into 3 sub-reactions. That first one is going to be the sublimation of carbon. All right, this step involves converting solid carbon to gaseous carbon, and the enthalpy change for this step is the enthalpy of formation of gaseous carbon. So the enthalpy for this first step is equal to the enthalpy change, the enthalpy of formation of gaseous carbon. So we're going to go ahead and write that down so that we remember, and that is something that we're given in the problem itself. This is equal to 715 kilojoules per mole. Now, the second step that we can write is going to be the dissociation of hydrogen gas. All right, the dissociation of hydrogen gas. And we can write this as having 2 moles of hydrogen gas to give us 4 moles of hydrogen in its gaseous form. So this step involves breaking the hydrogen-hydrogen bonds in hydrogen molecules to form hydrogen atoms. And the bond dissociation energy for one hydrogen-hydrogen bond is 436 kilojoules per mole. So then for 2 hydrogen-hydrogen bonds, the enthalpy change is going to be 2 times 436 kilojoules per mole. And this is going to be 872 kilojoules per mole. So let me block these 2 delta H's. Okay, and remember that we are taking two hydrogen molecules, all right, to form a total of 4 hydrogen atoms. We're going to need that because remember, our goal is the formation of methane, and methane has 1 carbon and 4 hydrogens. And now the last step that we can write is going to be the formation of methane from gaseous carbon, all right, from gaseous carbon and hydrogen atoms. So we can write the following expression. We can write that carbon in its gaseous form plus 4 hydrogen atoms give us methane. And this step involves forming 4 carbon-hydrogen bonds. Now, since the bond energy for one carbon-hydrogen bond is 415 kilojoules per mole, the total energy released, the enthalpy change, when we're forming 4 carbon-hydrogen bonds is just going to be 4 times minus 415 kilojoules per mole, and that gives us 1,660 kilojoules per mole. So again, let me reiterate here. The target reaction is split into 3 steps that involves the formation of methane from its elements in their standard states. We wrote the sublimation of carbon, we wrote the dissociation of hydrogen gas, and then we wrote the formation of methane from gaseous carbon and hydrogen atoms. And we were able to use the information we were given for the bond dissociation energies and for the standard enthalpy of formation. And now all we have to do for the second step is go ahead and sum up the enthalpy changes. So delta H for the reaction is going to be the sum of delta H of 1 plus delta H2 plus delta H3. So this is going to be 715 plus 872 plus minus 1660. All right, and that's going to give us about minus 73 kilojoules per mole. Of course, this can be easier if we round some of these numbers. We can round this to 700, we can round this to 900, we can round this to minus 1700, and you would get a value that's very close to minus 73. You would get something around minus 60, minus 65, something of the sorts. All right. So that is how we would approach this kind of problem. Wonderful. Now that we've covered these two example problems to help us solidify our understanding of Hess's law and standard enthalpy of reaction and formation, we want to go ahead and move into our next objective, which is all about entropy. Entropy is a fundamental concept in the field of thermodynamics, and it provides a measure of the disorder or randomness in a system. Now, the second law of thermodynamics deals with entropy, and it states that in any natural process, the total entropy of a system and its surroundings always increases. This is sometimes referred to as the principle of increased randomness or the principle of maximum entropy. And this means that systems tend to evolve towards a state of maximum disorder. So for example, if you have a gas confined in one part of a box, and then you remove the barrier, the gas molecules are going to spread out and fill the whole box. This is a more disordered or higher entropy state. Now, if you talk to any chemist or physicist, they'll tell you that they hate this definition of entropy, and it's better to think of entropy as the distribution of energy. In a high entropy state, energy is more evenly distributed, whereas in a low entropy state, energy is more unevenly distributed. So entropy is the measure of the spontaneous dispersal of energy at a specific temperature. You can think about this as how much energy is spread out, or how widely spread out energy becomes in a process. Now, the equation for calculating the change in entropy is delta S is equal to Q rev over T. Delta S is the change in entropy. Q rev is the heat that is gained or lost in a reversible process, and T is temperature. Now, the units of entropy are usually joules per mole times Kelvin, and when energy is distributed into a system at a given temperature, its entropy increases. When energy is distributed out of a system at a given temperature, its entropy decreases. Now, the second law of thermodynamics has also been described as time's arrow because there is a unidirectional limitation on the movement of energy by which we recognize a before and after state or a new versus old state. So, for example, you would instantly recognize whether a video recording of an explosion was running forward or backward. Another way of understanding this is to say that energy in a closed system will spontaneously spread out, and entropy will increase if it is not hindered from doing so. Now remember that a system can be variably defined to include the entire universe. In fact, the second law ultimately claims that the entropy of the universe is increasing. Now, entropy is a state function, so a change in entropy from one equilibrium state to another is pathway independent, and it really only depends on the difference in entropies of the final and initial states. In addition, the standard entropy change for a reaction, that's the delta S of reaction, can be calculated using the standard entropies of the reactants and products, much like enthalpy. And you can see that in this expression here. Now, as a final note, entropy also plays a role in determining the spontaneity of a reaction. The Gibbs free energy change, which is something we're going to talk about in the next objective, dictates whether a process is spontaneous or not, and it relates that to entropy and enthalpy changes. And that is a perfect segue into our last and final objective on Gibbs free energy. Gibbs free energy is a measure of the change in the enthalpy and the change in entropy as a system undergoes a process, and it indicates whether a reaction is spontaneous or non-spontaneous. Now, the change in the free energy is the maximum amount of energy released by a process that's available to perform useful work. The change in Gibbs free energy is defined in this expression. We have delta G is equal to delta H minus T delta S. Delta G is the change in Gibbs free energy, delta H is the change in enthalpy, T is temperature, and delta S is the change in entropy. Now, when delta G is negative, the reaction is spontaneous. When delta G is positive, the reaction is non-spontaneous, and if delta G is 0, the system is in equilibrium. Now remember that spontaneity doesn't necessarily mean speed. A reaction being spontaneous just means that it can occur without the input of energy, not that it's going to happen quickly. Some spontaneous reactions actually happen very slowly without the presence of a catalyst to speed things up. Now, both exergonic and endergonic are terms that describe different types of chemical reactions, specifically with regards to the energy changes that occur during those reactions. Exergonic reactions, this is when energy is released. This means that the energy of the products is less than the energy of the reactants. The difference in energy is released usually in the form of heat, light, or sound. An everyday example of an exergonic reaction is the burning of wood in a fireplace. The wood is the reactant, it contains chemical energy, and when it's burned during the reaction, it releases heat and light and leaves behind ash as the product, and ash has less energy than the wood. Endergonic reactions, on the other hand, absorb energy. This means that the energy of the products is greater than the energy of the reactants. The reaction takes in energy from its surroundings, and an example of an endergonic reaction is photosynthesis in plants. In photosynthesis, light energy is absorbed and used to convert carbon dioxide and water into glucose and oxygen. The product, glucose, has more energy than the reactants, carbon dioxide and water, because it took in light energy during the reaction. Now, what you see here is a table that shows the effects of the signs of delta H and delta S on the spontaneity of a process. Now, because the temperature in Gibbs free energy is in Kelvin, it's always positive. Therefore, again, the effects of the signs of delta H and delta S on the spontaneity of the process can be summarized in this way. When both delta H and delta S are positive, the reaction becomes spontaneous at high temperatures. This is because at high temperatures, the minus T delta S term becomes large and negative, which can outweigh the positive delta H, making delta G negative. Now, what about when delta H is positive and delta S is negative? Here, the reaction is non-spontaneous at all temperatures. This is because both delta H and this minus T delta S term are positive, making delta G always positive. What about when delta H is negative and delta S is positive? In this scenario, you're going to have a spontaneous reaction at all temperatures. And this is because both delta H is negative, all right? And then this minus T delta S term is also negative, making delta G always negative. The last scenario is when delta H and delta S are both negative. Here, the reaction is spontaneous at low temperatures. So you can think about this as delta H is negative, and this minus T delta S term is positive. And so to make sure that delta G is negative, you want the negative delta H to dominate. And this can only happen at low temperatures. Now, something else we want to talk about is the standard Gibbs free energy. The free energy change of reactions can be measured under standard state conditions to yield the standard free energy. All right, this is written as delta G of reaction. Now, for standard free energy determinations, the concentrations of any solutions in the reaction are 1 molar. The standard free energy of formation of a compound, that's going to be delta GF. This is the free energy change that occurs when 1 mole of a compound in its standard state is produced from its respective elements in their standard states under standard conditions. Now, like enthalpy and entropy, the free energy of the reaction can be calculated from the free energies of formation of the reactants and the products. So this is very similar to our equation for enthalpy and for entropy. Now, the last and final thing we want to talk about is the relationship between free energy, the equilibrium constant, and the reaction quotient. We can derive the standard free energy change for a reaction from the equilibrium constant for the reaction using this equation. Now here R is the ideal gas constant, T is temperature in Kelvin, and KEQ, this is the equilibrium constant. Now this equation allows us to make not only quantitative evaluations of the free energy change of a reaction, but also qualitative assessments of the spontaneity of the reaction. The greater the value of KEQ, the equilibrium constant, the more positive the value of its natural logarithm. The more positive the natural logarithm, the more negative the standard free energy change is. The more negative the standard free energy changes, the more spontaneous the reaction. Now, once the reaction begins, the standard state conditions no longer apply. The value of the equilibrium constant has to be replaced with another number that is reflective of where the reaction is in its path toward equilibrium. To determine the free energy change for a reaction that is in progress, we relate Gibbs free energy to the reaction quotient Q. And so we can write the following equation. Now, here, if this ratio of Q over KEQ is less than 1, if it's less than 1, then the natural logarithm will be negative. And the free energy change will be negative, so then the reaction will spontaneously proceed forward until equilibrium is reached. Now, what about if the ratio Q over KEQ is more than 1? If it is more than 1, then the natural logarithm will be positive, and the free energy change will be positive. In that case, the reaction will spontaneously move in the reverse direction until equilibrium is reached. Of course, if the ratio is equal to 1, then the reaction quotient is equal to the equilibrium constant, and the reaction is at equilibrium, and the free energy change is 0. So these are important to consider and remember, and we're going to do a bunch of practice problems to help us remember these points. With that, we've completed all of our topics for this chapter. I hope that it was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.